Welcome back everyone. In this lecture we will continue with the group action and we see various applications of group action. So let's begin. Let G be a group and X be a non-empty subset. So let's say G acts on capital X via some homomorphism tau. So then we define the following thing and we proved this orbit decomposition theorem. So what it says, okay, for given x in capital X, we have this orbit of x, that is all possible images of x under the action of capital G. So then we proved that the set of all orbits, so that will form a partition of this capital X. Okay. So in particularly, so we have, if we denote this x mod G by the set of all orbits of x, with respect to this action of G. So then we have the following decomposition of x with respect to this x mod G. Okay. So we often identify this indexing set with this x mod G. So that's what we did. Okay. The indexing set is chosen to be a subset of this capital X such that, so whenever you take this, so this is some subset of capital X. So let's write it again. So capital lambda is subset of X such that capital lambda intersection this orbit of X for any orbit. So that has cardinality exactly 1 for all x in capital X, or for all orbits in x mod G. So in particularly we have a natural bijection from capital lambda to x mod G. Okay, there is this natural bijective correspondence with capital lambda and x mod G. With this bijection we can identify capital lambda with x mod G. So then we can write x as disjoint union of all these orbits, okay, where this x runs over from capital lambda. So this is actually called orbit decomposition of capital X. Okay. So in particularly we were interested in particular type of decomposition. So we can collect those orbits that are having just singleton elements and those orbits that are having more than one elements. So for that purpose we defined what is called this capital lambda naught. So this is those x in capital lambda such that the size of the orbit is exactly 1 and capital lambda 1, or let us say capital lambda greater than 1. So this is those x in capital lambda such that the orbit having exactly more number of elements. Okay. So then with this notation we have partitioned this x into again further subsets. So you take orbits that are coming from this lambda naught. Okay. So these orbits OX, x is coming from lambda naught, and then disjoint union orbits where x is coming from lambda 1. Okay. So let me call this lambda 1. So now if you take element that is coming from this lambda naught, we see that this is if and only if the orbit is having just one element, if and only if all the elements of capital G that fixes this x for all G in G. So that means this x in lambda naught is nothing but all those x in Okay, this is if and only if x is in the fixed point subset of this action of g. Okay, that is x power g. So, in particularly one can rewrite this equation. So, one can rewrite this equation as follows. So, you can write x equal to x power g disjoint union orbit x, where x is coming from lambda 1. Okay. So, this is what we called orbit decomposition of capital X. Okay. So, now in particularly if the capital X is finite, so then we have the following observation. So, if the cardinality of X is finite, so then the cardinality of X can be computed as follows, which is exactly equal to cardinality of x power g plus summation all the sum of the cardinality of the orbits where x is coming from this particular indexing set lambda 1. So, recall that this lambda 1 is very important indexing set. This can be identified with those orbits coming from x mod g such that the cardinality of the orbit is exactly greater than 1, having more than one element. So, now recall what is this orbit stabilizer theorem. So, the orbit stabilizer theorem tells us how to compute the number of elements in the orbit. Okay. So, in particularly using this orbit stabilizer theorem, okay, from orbit stabilizer theorem, we have the orbit x, which is the number of elements in this orbit, is exactly equal to the index of the stabilizer of x inside this g, okay, which is exactly the cardinality of g divided by cardinality of gx if cardinality g is finite. Okay. So, we can also assume this g is finite set. So, g is finite group. So, in particularly the index is given by the ratio of cardinality of g divided by cardinality of gx using this Lagrange's theorem. So, in particularly if we know all information about the group, like the group we know and then all possible subgroups we know and then their order and so on. So, then using that information one can calculate the cardinality of given x. Okay. So, now by rewriting the orbit decomposition, we get the cardinality of x equal to cardinality of x power g plus summation the index, which is the ratio of this cardinality of g divided by cardinality of gx, where x comes from this particular subset lambda 1. So, where what is this gx? So, gx is the stabilizer of x, that is those g in g such that g actually stabilizes x, that means it leaves invariant g dot x equal to x. Okay. So, this is called the stabilizer of x. So, note that it is a subgroup and this is actually the index of that subgroup. So, now let us try to understand the connection between these stabilizers. Okay. So, this is actually very important equality. So, in this equality we need to understand this indexing set, this lambda 1. Okay. The lambda 1, recall this is those orbits. So, this can be identified with those orbits in x mod g such that this the cardinality of the orbit is greater than 1. Okay. So, now let us understand the connections between the stabilizers. Okay. So, for example, we can take some element in the orbit itself. Okay. Let us say some y is in the orbit of x. Okay. So, fix x in capital X and then take this y is in this orbit of x. So, in particularly y can be written as some g dot x for some g in capital G. Okay. So, now what we want to do, we want to actually relate these the stabilizer of x and the stabilizer of g. So, is there any connection between gy and gx? So if you think about it, the connection is the stabilizer of gy is given by the stabilizer of gx, the conjugate of stabilizer of gx. The conjugation is by this element g. So gx g inverse will be exactly gy. Okay, so let's prove this. So what is the proof? So the proof, so we prove that gy is contained in gx g inverse and vice versa. So now let's start with some element, okay, h in gy. So by definition, so if and only if h dot y is going to be y. So that is by definition. So that means what? If and only if you rewrite h dot g dot x is going to be exactly g dot x. So now what we can do, we can apply g inverse on both side. So if you apply g inverse on both side, from this what we get? So this star is equivalent to, by applying g inverse, you get g inverse dot h dot g dot x is going to be exactly equal to g inverse dot g dot x. But using the group action, so we can get this element by applying this particular element of the group g inverse hg on this x. On the right hand side, this is going to be g inverse dot g inverse g dot x. But g inverse g is nothing but identity. So this gives us that g inverse hg dot x is nothing but identity dot x, which is x. So that means, so this says that if and only if g inverse hg is an element of gx. So that means if and only if h is in gx g inverse. So all this argument can be reversible, okay, everywhere we have actually if and only if. So h is in gy if and only if we proved that h is in gx g inverse. So that means gx, the conjugate of gx, gx g inverse is same as gy. So that's what we proved. So we verified this. So this is very important observation. If you take two elements from the same orbit, then the stabilizers of them are very much related. They are indeed conjugate of each other, and the conjugacy is given by very specific element. Okay. So this is very important. So this actually tells from the combinatorial point of view, the cardinality of gx is same as cardinality of gy. So as a corollary, we get for any two element x and y in the orbit, okay, let us say this is one orbit, we have the cardinality of gx is same as cardinality of gy. Okay. So this is just some orbit. So that means if you know for some reason the cardinality of gx, and then if you look at all possible orbits of x, then the stabilizer of those elements will have the same cardinality. Okay. So that actually helps us to kind of compute the cardinality of x using this orbit decomposition. Okay, let us move on. So now we want to understand the kernel of this action. So this tau is a map from G to Sx. So as I said before, so given this group action, which is a group homomorphism from G to Sx, so this is actually a group homomorphism. So we can talk about the kernel of this group action or this homomorphism. Okay, so what is the kernel? So kernel by definition those elements of G that are mapped to identity map on X. Okay, so the kernel by definition those elements of capital G such that tau G is identity on capital X. So this G goes to tau G is the map. So this is a group homomorphism. So now if we rewrite the definition of this kernel, you can see that, so this is going to be those G in G such that G dot X is going to be X for all X in capital X. So that means, so this is going to be, so what is g dot x equal to x means? That means g is in the stabilizer of x. Okay, so so the condition on this kernel simply says that this g must be in the stabilizer of x for all x in x. So that means this is there in the intersection of gx x in capital X. Okay. So indeed what we proved, so the kernel of this group action or the group homomorphism is nothing but intersection of gx x coming from capital X. So this is what we have proved. So this is very important notion. For example, if the kernel is trivial, then we know that this map tau is actually injective homomorphism. Okay. So it is not hard to prove. Okay, I will leave it as exercise. Okay. So if you have a group homomorphism, let us say f from g to g dash. Okay, this is a group homomorphism. So then, okay, we have this following characterization of injective map. So f is an injective map. So that means this is a one-to-one map if and only if the kernel of this homomorphism is actually trivial. Okay. So one can take this as definition when you are dealing with group homomorphism, definition of injective map. Okay. This is indeed very trivial to check. So in particularly if you have the kernel of this group action is trivial, okay, then this G is embedded inside this Sx. Okay, this is very important phenomena. Okay, sometime if you are interested in understanding this group G, okay, so you make this group act on some very nice set capital X, okay, and then embed this group inside, okay, this symmetric group of that set capital X. So then using the information about the symmetric group, you can actually get more information about the group that you started with. For example, computations that you want to do in the group, okay, that can be done using the computations that we know how to do in the symmetric group, okay, between any two elements. Okay, so let us move on. So now we will see many interesting applications of this group action. Okay, so in particularly first I want to begin with the Cayley's theorem. Okay, which again talks about embedding a finite group inside some symmetric group. It's a very important result from the classification point of view. Okay, so let's state and prove. So we have this Cayley's theorem. So what it says? So let's start with the group G. Okay, so let G be a group. So then, so we have a natural map, so which we called it capital L. Okay, it is given by the left multiplication. So from G to the symmetric group on G. So this is indeed injective homomorphism. So this is called Cayley's theorem. Okay, for example, if you start with a finite group G which has cardinality n, let us say the cardinality of G is n, then we are saying G can be embedded inside Sn. Okay. So since n is fixed, so this immediately proves that as a corollary, okay, the number of groups of order n up to isomorphism must be finite, because any group of order n can be embedded inside Sn for that particular n. Okay, Sn is actually a finite group of order n factorial. So since number of subgroups of Sn is finite, so the total number of subgroups are finite, in particularly subgroups of order n, that also must be finite. So that implies that immediately the number of groups of order n up to isomorphism must be finite. Okay, that is immediate corollary. So, in case if you are interested in actually classifying all possible groups of order n up to isomorphism, then this theorem immediately implies that it is enough to classify all subgroups of order n inside Sn, okay, up to isomorphism. But that is not indeed actually very easy problem, it is actually very difficult problem. But Cayley's theorem immediately tells that the classification of order n groups, okay, up to isomorphism boils down to classifying all subgroups of order n in Sn. Of course, one can do it up to isomorphism, not a problem. Okay, but this question, even though it sounds like we have actually we have reduced the problem to Sn, still this is very hard problem. Okay. Okay, let us try to actually prove this map capital L is actually injective homomorphism. So, recall what is this map, okay. So, here is the proof. So, recall L is defined as follows. L is a map from G to Sg given by G goes to Lg, where Lg is a map from G to G given by x goes to Gx. So, it is basically a left multiplication. So, now we want to actually understand, we already verified this is indeed group homomorphism, okay. So, if not done, please verify, okay. So, verify L is a group homomorphism, okay. So, now we want to prove that L is indeed injective map, okay. Look at the kernel, what is the kernel of L? So, kernel of L is going to be those elements G in G such that Lg is identity map on capital G. So, what is the meaning of Lg is being identity map on capital G? That is if and only if Gx should be exactly equal to x for all G in G, okay. So, now note that we can particularly take G to be identity, okay, sorry, x to be identity. So, this is wrong, this is true for all x in capital G because G is given. So, for G in G, Lg equal to identity on G if and only if Gx equal to x for all x in G. So, now in particularly you set x equal to identity, then you get G equal to identity. So, now G is identity, then it is easy to see that Gx equal to x for all x in G. So, that proves that the kernel of L is exactly equal to identity. So, that means L is injective map, okay. So, that is simply Cayley's theorem. So, we can also reprove actually Lagrange's theorem, okay. So, let us revisit and then prove it using group action. So, here is Lagrange's theorem. So, we already proved it, but now we are proving this using group action. So, what is the theorem? Recall. So, G is a finite group and H is a subgroup of G. So, if this is given, then the order of H divides order of G. In particularly, the order of G divided by order of H. So, this is going to be exactly equal to the index of H in G. So, this is going to count exactly the number of left cosets of H inside G. So, this is what Lagrange's theorem. Okay, so now to prove the Lagrange's theorem, we need to choose the correct group and set capital X and then correct group action. Okay, obviously this is about the subgroup H. So we take the group to be H. So H is your group, and then your set X to be G, and then look at this right multiplication with respect to this H. So basically G to G we have a right multiplication, we will restrict that to H, that is the action H to SG. So where H is mapped to this right multiplication of H, which is a map from G to G given by G go to GH. Okay, so this is the action that we are talking about. So this is simply a right multiplication restricted to H, because we have this right multiplication from G to SG, and then the map is given by G goes to, let us say, RG, where RG is a map from G to G, where X goes to XG is what given. Okay, you restrict R to R restricted H, so that is your RH. So now you can see that so X will be disjoint union of cosets, sorry, union of orbits. So with respect to this action, okay. So with respect to this, so let's look at the orbit. Okay, for example, orbit of the identity is going to be, so all possible images of this identity. So which is going to be EH, H in H. Okay. So by definition, this is exactly, okay, let me write it. So by definition, this is exactly this RH of H applied on this identity. So that is going to be just EH. Okay, so let me rewrite because some confusion. Maybe you can take it as exercise, just prove that by definition the orbit of identity is nothing but EH where H in H, so which is exactly equal to H. So now if you take any other element orbit of G for G in G, you can see that this is going to be just GH where H comes from H. So this is exactly the coset G capital H. So in particularly, so this union of the orbits will be disjoint union of all these cosets where G comes from this X mod H, which is G mod H. Okay. So now you can see that using this orbit decomposition theorem, the cardinality of X, which is cardinality of G, is exactly equal to summation the cardinality of H, where the sum runs over exactly k number of times, where k is exactly the cardinality of G modulo H. So that is because the cardinality of GH is same as cardinality of H for all G in G. Okay. So then this sum runs over k number of orbits. So exactly it is going to give you k times the cardinality of H. So that is what we wanted to prove. Okay. So the number of left cosets of H in G, which is k, is equal to the index of H in G. Okay. So we got these two immediate theorems as corollary of group actions. Okay, we will actually see later many interesting corollaries. So I will stop here. We will continue in the next class.